anything, no air resistance. I didn't label this, but they're held apart by a distance x. So somebody's holding the ball and the earth apart, and then they're released, and the ball falls toward the earth, and the earth actually moves toward the ball. They're pulling on one another. And I drew it upside down because the ball in this perspective is going to go toward the earth, and that would be falling. But we could look at the earth from this perspective. That's all okay. This is repeated with a variety of balls. So not this one, a different one, and then a different one, and a different one. But they all have the same mass, and they all have the same radius, and they're all separated from the earth by the same distance. So number one asks you to describe some types of balls that would produce the highest and lowest impact forces when they collide with the earth. So if you chose, several different balls to release from this position, they're going to hit the earth's going to hit the ball. Describe some that would produce the highest impact force and lowest impact force. Think about that. And then number two is going to be the same kind of question, but the question will be, what kind of ball is going to produce the largest and smallest change in momentum? Or maybe I should have said result in the largest and smallest change in momentum. Does anybody have an answer for if you wanted to insert a ball here that would give you the greatest impact force, what kind of ball would you use? If you're at home and you want to answer, raise your hand. Anybody here? Heavy one? Well, they're all the same mass.
Oh.
And the distance to the earth is the same, so their weights would be the same.
What are your options?
Anything you want, as long as it's got the same mass and the same size, and you're holding it the same distance from the earth. So this could, in the classroom, this would look like, I had a ball here, I could drop it, I could get a different ball and drop it. Emma, what do you think? Say that again, a little louder, I can't hear you. Oh, the radius is fixed. So we've got constant mass, constant radius, and constant distance from the earth. So you're right, if it were a smaller radius ball, then it would fall farther, right? But that's been disallowed in this question. Canizaro, what do you think? Get ready, brace yourselves for the noise.
Wouldn't it be velocity or no?
Well, I'm asking, what kind of ball would you drop if you wanted to have a big impact force?
Bouncy ball.
A bouncy ball?
Yeah. No, bouncy ball.
So, okay, I've heard bouncy ball and hard ball. Let me turn up the volume. For some reason your volume is low. I don't know if it's just you or... Oh, you know what? I bet somebody turned the volume down on this thing. It's usually super loud. No? Let me test it. Must just be Jack. Okay. So, sorry Jack, I lost what you were saying. So the answer is either drop a hard ball or a really bouncy ball. Now you could have a really bouncy ball that's a hard ball, but let's say all that you change about it is which one is most obviously going to make the biggest force? Hard or bouncy? How many people think it's hard? Raise your hands. Okay, how many people think it's bouncy? And I would side with the hard ball. Now there's a little more to it, because it's kind of, actually, you know what? This is really complicated. I could make an argument. So this is actually spoiling my my sequence. So see how at number 4 it says go back to number 1? Well, I don't know if by the time we get through this I'm going to want to go back to number 1. Let's see, what can I do? I'm rigging up my other camera, which I don't even have connected, so no wonder it's not showing up yet. All right. So here's the ball, and here's the earth, and it's going to hit. And so I want to hear Wyatt. Why do you think a bouncy ball? So if this ball hits the earth here and then it bounces away really high, why do you think that's going to make the force bigger?
Because to bounce away, the ball has to push on the earth, wherever it is.
Yeah. So in order to, if it just hits and it doesn't bounce, then it's sort of, there's one push going on. But if it hits and then it bounces away, it's like it's pushing the earth and then it's getting pushed again away. But another way to think of that is the momentum. If you just have a ball that hits and it stays there, then this has a small change in momentum. It's going from some velocity, it's going faster and faster and faster, and then it's stopping. This has a big change in momentum because it's got a lot of speed, and then it reverses directions. So change in momentum equals force times time. And change in momentum equals force times time. So if you have a small change in momentum, the product of force times time is going to be small. And if you have a big change in momentum where the thing reverses, the product of force times time is going to be big. Now, you could have force times time be really big, but the force could still be really small, right? So this could either be, so let me write it like this. I'm going to make a big delta P. And there are three options that I'm going to show. There's sort of a medium force, medium time, gives you a big delta P. Or you could have a little force over a big amount of time, which could give you a big delta P. Or you could have a big force over a little time, which could also give you a big delta P. Now over here, I've got a little change of momentum, so let me make sure my delta P is small. One way to accomplish this is to have sort of Ft like that. One way is to have pretty big force times a little tiny time. And another way is to have a little tiny force times a pretty big time. So this is really complicated, but it's possible to have a bouncy ball that has a big change in momentum that still has a small force. And it's also possible to have a ball that's not very bouncy, that doesn't have much of a change in momentum, to actually have a pretty big force. So the bouncy part is maybe relevant. What kind of a ball would actually, like the biggest force of all would be the bouncy ball that has a big force over a short time. Now, is this a hard ball or a soft ball? This is a hard ball. So if something like, if it's made out of this maple and it hits, the time of impact is going to be really small, so that means the force has to be really big. And if the ball is made out of something soft like this towel, it's not going to just suddenly hit. The time of impact is going to be longer. It's going to have a small force. So the answer to that first question, I actually, going back on it, I like both answers. I like a hard ball, because if you have a hard ball, the time of impact is short and the force is big. That's the answer I was looking for. But I also like the bouncy ball because, you know, if you have a really hard ball in this situation that doesn't bounce back, you can get a pretty big force, but you'll never get as big a force as if it bounces off. Because in this case, the product of force times time is bigger than the product of force times time over there. All right, so I apologize, Wyatt. That was a good answer too. Go back to the questions here. Describe some types of balls that would experience the largest and smallest changes in momentum. So, real quick, number one, what I was expecting was, with forces, I was expecting something with like a short impact time and long impact time, which depends on whether it's hard or soft. The second one, I think we've already been over this. What kind of ball would experience the greatest change in momentum? So if I release this, I let it hit the earth, what kind of ball do I want there? A bouncy ball or one that doesn't bounce? Which one's going to change momentum more? The bouncy ball, because it's going to go from an upward direction and then reverse course and go downward. So it's going to have a positive velocity that switches to a negative velocity. That's a big change. If it doesn't bounce at all, if it just thuds and stays there, it's going to have a positive velocity that just goes to 0, which isn't as big a change. So bigger change in momentum if it bounces. Number 3, describe the types of balls that will produce the highest and lowest impulse during their collisions with the Earth. So if I let a ball go, what kind of ball do I want to drop to have the lowest, the highest possible impulse? This should be an easy one now that we've already talked about everything else. The bouncy kind, because impulse is change in momentum. I'll uncover what I wrote. I think I wrote that before. This is force times time is impulse, and that equals the change in momentum. Change in momentum equals impulse. So this is really the same as the previous question. Whichever one has the greatest change in momentum is going to have the greatest impulse. The greatest impulse? Not necessarily the greatest force, because it could be a soft, bouncy one where the impact time is really lengthened so the force is small. And then if you have one that doesn't bounce, its velocity would change even less. Now, can you think of a situation where you drop a ball, it hits the Earth? This is really weird. In fact, if you're stuck with a sphere, it might not work. But can you imagine a thing that drops, heads toward the Earth, and then its velocity or its momentum changes even less than it would have if it stopped? So I've been comparing the ball bouncing off versus the ball just hitting and stopping. And the ball bouncing off has the greatest impulse, greatest change of momentum. The ball stopping has a lower impulse and lower change of momentum. Can you think of something with, what would the ball have to do to have an even smaller impulse than that?
Go in.
It would have to go in. Yeah, if this were a really, really sharp arrow, super duper sharp, and it could actually impale the Earth and maybe even like squish on through, then that would even have a lower impulse and smaller change momentum. But I don't see how a ball could really do that. So here we are at number 4, which is where we were supposed to go back to number 1 and then make it get complicated, but we got complicated in the beginning. Number 5, compare the Earth's experience to the ball's experience in terms of impact force, impact time, impulse, and change in momentum. Meaning, for example, which one experiences a greater impact force? Or which one experiences less impact time, or a stronger impulse, or a greater change in momentum? How about impact force? Which one gets hit harder, the ball or the Earth? Same, yeah. Newton's third law says you can't have one force exerted on an object be stronger than the force that the object is, if you have two things, they're going to exert the same force on one another. So they're the same. How about the impact time? Which one gets hit longer, the ball or the Earth? Same. Okay, so you can't have two things hit each other for different amounts of time. How about impulse? Which one experiences a greater impulse, the Earth or the ball? Not the ball. Not the Earth. What is impulse? If I'd said, give me the formula for impulse, what would it be? Force times time. And if the force is the same and the time is the same, the impulse is the same. So now the change in momentum. Which one experiences a greater change in momentum?
Same.
It's the same too, because impulse equals change in momentum. Now if you wanted to be kind of a smarty pants here, I'm talking absolute values, but the forces would be opposite. So if the ball experiences a downward force of the Earth pushing it down, that'd be kind of a negative force, and the Earth is experiencing upward force by the ball. I guess in that way you could say that the ball's force is negative, so it's less than the Earth's force, but aside from that, everything is equal here. They both change momentum the same amount, which means the well, let me not spoil number 6. Visualize a graph of momentum versus time for the entire system. So I'm going to set up a graph. And visualize what it would look like if I filled it in. So this is the entire system of the Earth plus the ball. This is momentum. This is time. This is 0. Anybody have an answer? How would I draw this? So here, just to add a picture in here in this part, there's the Earth. Here's the ball. I let them go. Then a moment later, the ball is heading toward the Earth, and the Earth is heading toward the ball. And then a moment later, they hit each other. As this happens, as the ball falls toward the Earth, what's going to happen to the momentum in the system? It's going to and it'll stay the same, but what value will it have? How many kilograms meters per second? If I hold the Earth here, I hold the ball here, and then I let them go. The momentum is going to be the same forever after, but what's it going to be? 0. Yeah. Momentum is always 0. And it's always 0 because I'm holding them still in the beginning. So the momentum of this is its mass, which is really big, times 0. It has no momentum. Momentum of this is a really small mass times 0, which is no momentum. So the entire system has no momentum. And according to the law of conservation of momentum, it's going to keep no momentum. So as the Earth starts to gain negative momentum, then the ball would gain positive momentum. And if you add those together, you get 0. So the total momentum can't change. Hopefully, thinking about these questions, this might be a good thing to go back and think about when you're getting ready for the test. There will definitely be some kind of tricky questions about this stuff, plus coefficient of restitution. All right. Plan for today. Test review. Well, we need to go over the homework. If anybody, I think I assigned the rest of the problems for. Actually, did I? I really didn't assign anything except optional. No.
Multiple choice.
I didn't put it on here, but yeah, multiple choice. You were supposed to do the multiple choice section of Mr. Pennington's old test. So let's just talk about that first in case anybody has any questions about it. And then I'll tell you more about the test and kind of the plan for the rest of the year. And then we can start on torque, which is really nice. In my experience, when we begin torque, everybody thinks, oh, this is just so nice. I can do this. It makes total sense. And when we get to the test, everybody's forgotten all about how to do torque. How do you do that again? So these were the multiple choices. Anybody have any questions about any of these? Or if some of you decided to do Mr. Pennington's old test and have any questions about that, I could talk about that too.
For number 6, it's...
This one?
Yeah, it's asking for the walls in number 4, but the answer is springy wall, but isn't the walls in number 4 the hard and the soft wall? I'm confused with that.
Yeah, well, I think it should have just said consider all the walls. So right. I don't know. It should have just said consider all 3 walls. Sorry about that. Consider all of the walls. That would have been better. Do you want me to explain that or?
No, I
okay.
I get it now. But...
Jack Canizaro, what's your question?
For number 4, I was confused.
Okay. curious about why my camera just went off. So can you see my screen still?
I can see your paper, I can't see your screen.
Right. So you're seeing my screen. You're just not seeing for some reason my webcam that's got a picture of me, you're not seeing that. That went away. I don't know why. And what was your question? I just totally forgot. 4?
Number 4.
Okay. So just to set this up, we've got 3 different walls or eggs or whatever. The first wall, so this is the really hard one, and I'm just going to show the egg kind of hitting this, and this is my animation of the egg getting splattered, and then everything's basically going to fall on the floor, drip to the floor after that. And the second one hits a soft wall, which I'll just represent that as maybe a sheet. You can do this with a tarp. If you want to throw an egg at something really hard and have the egg not break, hang a tarp from the ceiling and throw an egg at that, so that the egg will hit the tarp and then it'll stop, but it'll fall to the floor and then it'll break, unless you put some padding on the floor. So this is hard, this is soft, and then the last one is springy. So this wall I'm just going to draw as having some kind of big spring behind it, and the egg comes in and it hits the wall and then it bounces off again, so it bounces in the other direction. And compared to the first egg, the hard wall, the second egg, the soft wall, experiences. So both of the eggs start out with a certain velocity. V0, I'm just going to say is, well, these are equal. They're going the same speed. So when they hit the wall and they both stop, they both lost the same momentum. So the change in momentum for this and the change in momentum for that are the same. And the change in momentum equals the impulse. So these are going to have the same impulses, which is force times time. But since it's really hard, this is going to come to an abrupt stop. So maybe for this one, it's going to look like this. Delta P equals little tiny time times a big force. And for this one, we're going to have the same change in momentum because it's going the same speed and then stopping. This is going to stop over a bigger time, so it's going to have a small force. So in both cases, the momentum change and the impulse, which is the product of these two numbers, is the same. But the difference is that the one with the hard wall has more force. So compared to the hard wall, the second one experiences less force and the same impulse. And the only way to experience a different impulse is to have a different change in momentum. To somehow not slow down as much, or to somehow reverse directions and change velocity more. This is the one with a different impulse. This is the one with more impulse than the other two. How about that, Jack? Okay. Other questions?
You do number 5 on the
problems?
Other one.
On the practice,
Yeah, the
Mr.
problem.
Pennington one? Yeah, let me go find that. So, multiple choice 5 or
No, the
problem 5?
I get confused by like the M1.
Oh, okay. I'll open up his solutions at the same time. This is happening these days. Looks like nothing's there, but then it loads, and after a while I get it. So I'm going to his solution first. Oh, great, I've got his problem and the solution here. So, problem number 5, we've got a falcon and a dove. And we've got the mass of both of them, and the falcon is chasing the dove from behind in midair. What's their velocity after impact? If the falcon's velocity is 26 meters per second and the dove's is 6 meters per second in the same direction initially. So let me go down to what he did there. This is a classic conservation of momentum problem. And the simplest way to state the conservation of momentum, let me get my pen out. I could draw on this. Have to snip the screen though. All right, come on. Get this color. So this is the really simple version of the law of conservation of momentum. It just says that the initial momentum in a system equals the final momentum. And this is only if there's no outside force, and there isn't. There's nothing else pushing on the hawk or on the, what was it, a dove that it's chasing. And then this is the more complicated way to write the law of conservation of momentum. So we've got a mass of one object times its velocity plus the mass of the other object times its velocity added together. That gives me the total momentum of the whole system. And that has to stay constant. Now over here on the right, he could have written this, instead of writing it just like that, he could have said this is M1 V1 final plus M2 V2 final. But he lumped everything together into just one object, because when the hawk right here grabs onto the dove, they're going to become one thing moving together, and they just have one velocity. So you could do this, you could do it this way, and you could use the hawk's mass times its new velocity plus the dove's mass times that same new velocity, and the algebra will work out the same way. This should say, well, these would be the same. So are you okay with that part so far?
Yeah.
Okay, so once he sets this up, let me just erase all this stuff. Once he has all that set up, this is just the same as that. He's just dividing everything by M1, M2 to isolate final. And then he plugs everything in. So this is the mass of the hawk times its velocity, that's M1, V1. This is the mass of the dove times its velocity, M2, V2 initial. And then this is their total mass afterward. It'd probably be more understandable if he had just plugged everything in here and then solved.
Yeah, I get
Okay. Other questions? Anybody have any other questions about either thing? If you think of any as time goes on, we can come back to this. So let me tell you about the test. Oh, and by the way, you can see I've updated my website to the 12th of April. And that'll be the week before spring break. We'll have a test on that Monday. And if you want to know what we're doing between then and now, you can look at all this stuff. So we're right here. Right, here's what to expect from the test. No multiple choice. It's kind of unique. I usually have multiple choice questions.
This one?
What's that?
This one is no more?
No multiple choice. There are going to be 3 short answer questions with multiple parts. So be ready for that. That'll really take care of a lot of the kinds of things I usually ask in multiple choice questions home in on. 5 problems, 22 points in all. So if you add up the points, 10 points, 22 points, this isn't really a very long test. And I probably won't count it as much as the next test. The problems, you're going to have a straight momentum problem where you just plug and chug with this formula, momentum equals mass times velocity. You're going to have something where you have to apply the impulse formula. Conservation of momentum, there's going to be one ballistic pendulum problem, and then there's going to be a problem with a collision and a coefficient of restitution. Sources of questions and problems, the entire packet, notes, practice problems, and the so-called labs. So make sure you understand how ballistic pendulums work. I'd go over the notes related to that, and then also the collision stuff with about the carts. Make sure you understand the answers to those questions. Especially important concepts, the relationship between impact force, impact time, change in momentum, and coefficient of restitution during collisions. We did a lot of that in the warm-up today, but we didn't really talk about coefficient of restitution. law of conservation of momentum, when you can apply it and how you can apply it. So sometimes it doesn't apply because there's an outside force, and momentum actually changes, or total momentum in a system. Coefficient of restitution, know what it means and know how to apply the formula. And I don't know why I wrote types of problems again, but these are the formulas. So the new ones are here: momentum, this is conservation of momentum, this is impulse, this is coefficient of restitution. But for the ballistic pendulum, you're going to need to know these: 1/2 mv squared, mgh, and the law of conservation of momentum.
Are those going to be given?
Yeah, I'll give all these to anybody who wants them, but if you want to memorize formulas, make sure you know all of those. Let's see, let me go back to here. I guess that's it. Does anybody have any questions about the test? No? All right. Well, if you think of some before class is over, ask away. But let's start on torque, which again, I think you'll feel like, oh, this is kind of nice algebra. It's simple, it makes sense, it's works out well. People at home, if you don't have this packet, I'm sorry. You'll just have to follow along, or you can print this page out. I've got plenty of copies in the room, and you all have one, right? Okay. So that symbol right here that Mr. Pennington likes to use, I think he tries to get away from a capital T. So the symbol for torque is a tau, technically, but a capital tau looks like a capital T. And I think he's afraid that if he uses a capital T, people will think it's what? What's it? Time or period, because we've used it for other stuff. And so its symbol is, I'll try to write it as a squiggly T, which is a tau. And does anybody know what tau means in math? Tau is 2 pi. So there are a lot of people, there's this big movement. If you Google tau versus pi, in fact, if you look up the symbol for it, pi kind of looks like this, and tau looks like half of a pi, which is the opposite, because it's 2 pi, right? Yeah. So that's kind of confusing. Anyway, there's a raging debate over whether we should get rid of pi and just use tau, because it would be simpler. So the rotational equivalent of force is torque. So before, we would have a force that pushes something in a line, but now we're going to have torques which cause things to twist. So this is twisting around an axis. There's some torque acting on it. Up until now, we've just had things moving this way, or in odd directions. But all these motions are going to be circular. And an example of torque is if you have a nut that's on a bolt, and you've got a wrench here, you can apply a force in this direction. We'll be referring to this as the applied force. And it's important, if you want to know how much torque you're getting or adjust the amount of torque that you have, that you adjust your lever arm properly. So R, which is called R because you can think of it as the radius from the center of rotation to wherever the force is applied. If you have a longer lever arm, you're going to get more torque. If you have a shorter lever arm, you're going to get less torque. So this is the lever arm, and it's the distance force is applied from the rotational axis. So I don't know if anybody's ever had trouble. You've got a bolt where the nut is just rusted on and you can't turn it. Does anybody know a trick? If you can't do it with this wrench, what can you do to get some more torque? what kind of wrench would work better if you can't get that nut off with this torque? Or sorry, with this wrench.
Torque wrench.
Well, a torque wrench will allow you to measure the exact torque. So a torque wrench has got a little, some kind of a gauge in it, so that as you push on here, it'll measure your force and calculate the amount of torque that you're applying to this nut. But if you want to just increase the torque, yeah. So what I do is I get a pipe, and I try to find a pipe that I can put around it, and then I push over here, and then you can get a lot more torque that way. So torque equals the length of the lever arm times the perpendicular force F. And if this force is perpendicular to the lever arm, then you can just do F times R. But sometimes they're not perpendicular, so the more general case is this. Torque equals R F sine theta. And that means this. So if this is R, this is the lever arm, and this is the force, this is theta. And I guess I should say this is the rotational axis. So, and you know what, it might actually be better if I didn't draw it looking like it's always a 90-degree angle. So there's my force. You can keep it a 90-degree angle if you want. So when theta equals 90 degrees, in that particular case, when this is a right angle, torque equals RF. And when theta equals 0 degrees, so if instead of pushing your wrench this way, what would happen if you pushed this way on the wrench? How much torque would you get on that nut then? How good a job would you do of twisting this wrench if you just pushed this way? Terrible. Or if you pushed this way, it wouldn't work either. So when theta is 0, the torque equals 0. When theta equals 180 degrees, the torque is also 0. So ideally you want to push perpendicular to the lever arm. Torque is at a maximum when theta is 90 degrees. Now for what I consider to be the pleasant part. This is all about balancing torques. And rotational equilibrium, there can be a couple of kinds. Rotational equilibrium happens when net torque is 0. Just like when net force equals 0, this would just be regular equilibrium. You don't have to write that down, but when the net force acting on an object is 0, then there's no acceleration and things are in equilibrium. You can have dynamic equilibrium or static equilibrium, which either means something's moving at a constant speed or it's not moving at all. And in the case of rotational equilibrium, when the net torque is 0, that just means that this is either still and balanced or that it's tipping, but it's tipping at a constant rate. So all these problems are about how do we get this system to balance. And the way I'm going to do it is a little bit different. If you look at Mr. Pennington's notes, he likes to start out saying clockwise torque equals counterclockwise torque, but I like to do it the other way, and I'll explain why. So I'm going to start out with counterclockwise torque equals clockwise torque. So this is the condition for rotational equilibrium. If we want to balance this thing, then whatever is tending to twist this counterclockwise like this has to be equal to whatever is tending to twist it clockwise like that. So this is a really easy one with just using common sense. If this is the fulcrum, so it rotates around this axis, we've got 100 Newton weight over here 2 meters from the center. We've got some other weight 2 meters from the center or to the right. What does this weight have to be? What's that?
100.
It's got to be 100 also. But so you could just guess this, but I'm going to work through the math of it, and then things will get more complicated. So to add up all my counterclockwise torque, I'm going to do this is R, 2 meters, times the force, which is 100 newtons. That's the counterclockwise torque. And that equals the clockwise torque, which is 2 meters times whatever that is. I'll just call it 2 meters times x. I don't know, I don't really like x, but I'll call it force, F. So this is 200, guess what, oh, did I go over the units for torque? I guess I didn't. So guess what the units are? Nm, Newton meter. And way back when we were talking, when I was saying that work is often written as newtons dot meters, that's, I think, to distinguish it from torque. But Newton meter is the word for it. If you have a torque wrench, if you work in a shop, it's usually in foot pounds. So it's a unit of length multiplied by a unit of force. So that equals 2 meters times F. So F equals 200 Newton meters over 2 meters, which is 100 newtons, which we knew from the beginning. All right, gets a little bit more complicated here, but not much. So the counterclockwise torque needs to equal the clockwise torque. And in this case, my counterclockwise torque is going to be, it's caused by this force pulling down over here. So it's the same as it was before. The lever arm is 2, the force is 100, so it's going to be 2 meters times 100 newtons, which is going to give me 200 Newton meters. Before I even do this, what does this weight need to be? 50? Well, how do you know?
Mental math.
Yeah, well, you can either do all this ahead of time, or you can just think, if you want to balance these and you make this sticking out twice as far as that, if you put the same weight out here sticking out twice as far, it's going to tip. So for most people, it's common sense that this needs to be lighter. And maybe since it's sticking out twice as far, it needs to be half the weight, which is the case. So on the right, the lever arm's 4 meters, and the force is what I'm looking for. So 200 Newton meters equals 4 meters times F. So F is 200 over 4, which is 50. Number 3, got to figure out this length right here. So I don't think this is really all that hard either. We will get to a tricky one in a little while. So I just start out the same way as usual. Counterclockwise torque equals clockwise. The counterclockwise torque, I'm going to call this R because I don't know it, times 800. And the clockwise torque is R times 600. So R times 800 equals 2400 newtons. So R equals 3 meters. That might have been a little bit tougher if you had just looked at it and thought, I don't know, this, since that's heavier, this needs to be a little bit shorter, but how much shorter? I'm hoping for a tougher one here. This isn't, it's not too tough, but we'll do it anyway. So if you've got a 5 meter beam that weighs 500 newtons, and we're trying to hold it level by applying a force here, what does the force need to be? So this is a 500 Newton beam, and it's supported on this end. How much force do you think you have to apply right there to hold it up? Anybody want to guess?
2500.
What's that?
2500.
2500? Any other guesses? 100? Any other guesses? 250? All right, well, let's see. So first, you can assume for all these drawings that if there's a dot like that, that's the center of mass of the beam. So we'll just assume that the weight's evenly distributed throughout the beam. So we could picture this beam as being like no weight, and then a weight hanging off of it right here that's 500 newtons. So if you just imagine a 500 Newton force exerted right there. So I'm going to do counterclockwise torque equals clockwise torque. And what's my counterclockwise torque here? Which one of these two forces is going to make this thing rotate counterclockwise? The 500 Newton weight of the beam or the force that we're applying to the beam? This. So there's the axis of rotation. So it's going to go like, this is the counterclockwise torque. So it's going to be whatever that force is times the length of the beam, which is 5 meters. That's the torque that's being applied, counterclockwise. The clockwise torque is going to come from this. It's making the beam go like this. So 500 newtons is the force. What's the lever arm? How far is this? 2.5 meters. So I get F times 5 meters equals 5 times 2.5, which would be 1250. And is that 1250? Yeah. So 1250 divided by 5 is 250. So you're right, Sam. So if you think about that, if you just want to hold it in place, it's like two people holding it up. One person's holding on the right, one person's holding on the left. And if they both apply a 250 Newton force, then they can hold it up. All right, now it's going to get, this is graduation. Find the force needed to hold the actually, yeah, it seems like I want to do one that's a little bit harder though after this. Find the force needed to hold the same beam level with the addition of a hanging weight. So I want to know what this force needs to be. And this is 500 newtons. Why don't you all try to do this? I'm going to, wish I could just pause for a second. I'm going to move my camera so it's pointing somewhere else and I'll do the work. Mm-hmm. Does anybody have an answer to share? Jackson, what'd you get? 290, yeah, that's what I got. So if you're still working, you can keep working, or you can look at my work here. Added up all my counterclockwise torques, and there's really just one. This force is the only force that's going to make us rotate around the axis counterclockwise. So that's F times the length of the beam, because it's the same beam, times 5 meters. But then clockwise, there are two sources of the torque. There's the weight of the beam, which is going to act right here at its center. It's 500 newtons. So that's 500 times the length of half the beam, 500 times 2.5. And then there's also this weight, which is going to make everything rotate clockwise, which is 100 newtons times 2 meters. So I need to add both of these clockwise torques together, and that ends up being 200 for this one, 1250 for that one, so 1450 total. And 1450 divided by 5 is 290. So that's all the ones that Mr. Pennington really includes in his notes. Your assignment is to do the torque practice, and you just need to do this by Monday because we've got the test tomorrow, and I don't want you to worry about this too much. But I do want to do at least one or two more with you. I think these are fine. These, okay, these are a little bit tricky. And I'm going to jump in and just do B, or we can do B together. Yeah, all right. So in this kind of a problem, it says find the location of the fulcrum. So where do we need to put the fulcrum? Where do we need to put the balance point to make this beam balance? This one's kind of easy, actually. And actually, maybe it's not so bad. So what would you guess if you were just looking at B? Like, would you put the pivot point there? Would you put it right in the middle? Would you put it over here? Over on the right, you think? So what would happen if you put it right in the middle?
Right. Yeah, on the right.
So
The left.
I've done this a lot of different ways, and it seems to me that even if you have really bad insight, this ends up working out. So if your guess about where that needs to go in the first place is ultimately wrong, it doesn't really matter as long as you do the math right. But you need a guess to get started. So just think about this to begin with. If I put this right in the middle, then this weight that's hanging in the middle, that's not really going to do anything. That's not going to tip it one way or another. So I've just got this heavy weight over here, and light weight on the left. Which one's going to have the stronger effect, the 400 newtons or the 200 newtons?
400.
The 400. So if I don't want this 400 to tip it down, where do I need to put my balance point? Do I need to put it closer to the 200 or closer to the 400?
400.
Probably closer to the 400. Now, if you guessed that I think we should balance it here, you can still do the math here and it'll still work. It'll just look a little bit different. But what I'm going to do is I'm just going to preliminarily put my fulcrum there. I'm also going to plug in my computer and then work through this. If you think you know how to find the location of the fulcrum, go ahead and try to stay ahead of me. But if you want me to take you through it, I will. The secret to it, or the crux of this whole thing, again, is just balancing torques. So I'm just going to start like I've started everything else. Torque counterclockwise equals torque clockwise. But if I don't decide where exactly this is, or come up with some ways to describe these distances, then I can't calculate any torques. So I'm going to introduce a variable. It could be, well, there are a whole bunch of them that I could use. I could say this is x if I wanted to. And if that's x, then what would this distance be? Yeah, so it'd be 5 minus x. And so, maybe it would be easier to call this x. So if I call that x, then this is 5 minus x. And this is, this whole distance is 5 plus x. I kind of like that better. So I'm going to call this the distance from my fulcrum to the center. I'll call it x. And since the center to here is 5, this is going to be 5 minus x. And since this is 5, then this whole distance here, that's going to be 5 plus x. So now I can do it. I've got all the distances that I need. So for my counterclockwise torque, I'm going to have two things tilting this counterclockwise. There's this force and this force. So this 100 Newton, the torque is going to be that force times x. X times 100 newtons. And this is going to give me 200 newtons times 5 plus x. 200 newtons times 5 plus x. And then for my counterclockwise torque, there's just that one. So the force is 400 newtons, and the lever arm is 5 minus x. So now it's just algebra at this point. This is 100 newtons x. This is 1,000 Newton meters plus 200 newtons times x. And this is 2,000 Newton meters minus 400 Newton x. So I'm going to combine all my Newton x's on the left side because I've got 100 here, and then I've got 200, so that's 300. And then I'm going to add 400 more, so I get 700 newtons x. And then over here, I've got 2,000 Newton meters and 1,000 over there, so I'm going to subtract this from both sides. So to solve for x, x is going to be 1,000 Newton meters over 700 newtons. So 10/7 of a Newton, or 10/7 of a meter. Assuming I did all that right. I have to check my answer key to see if that's correct, but that's the right method. Whether I actually did it correctly and got the right answer, I'm not totally sure. Let's peek and see. I would guess that Mr. Pennington had his he might have had his solution described differently. This one, wasn't it? So he's saying it's 1.43 to the right of the center. Is 1.43 the same as 10/7?
Yeah.
Okay. Yeah.